There is one number that governs everything in the universe, not a law, not a rule, a hard boundary baked into the fabric of space, time, and causality itself. Cross it, and time runs backward, cause follows effect, and reality tears itself apart. Today we uncover what the speed of light actually is, why nothing can ever break it, and why without it you would never have existed at all. Now let's begin. The sun you see right now is not real, not in the way you think. The light hitting your eyes at this very moment left the sun 8 minutes ago. 8 minutes of travel across 150 million kilometers of empty space, arriving here, landing on your retina, and telling your brain, the sun is there, the sun is shining, everything is fine. But the sun you are seeing is a ghost, a portrait of something that existed 8 minutes in the past. If the sun were to explode at this exact second, silently, violently, completely, you would not know. You would keep reading, you would keep breathing. You would sit there perfectly calm, watching a star that no longer exists for 8 full minutes before the last light finally stopped coming. That is not poetry. That is physics. Now look at the night sky. Find Sirius, the brightest star you can see with the naked eye. The light reaching your eyes tonight left Sirius roughly 8.5 years ago. That light was already traveling through space when certain world events were unfolding in your own life. Whatever Sirius looks like right now at this actual moment, you will never see it. No telescope, no technology, no future civilization will ever show you Sirius as it is today. By the time that image arrives here, another 8.5 years will have passed, and today will be long gone. The night sky is not a picture. It is a collision of different moments layered on top of each other, all arriving at your eye simultaneously and pretending to be the present. The star, 3 degrees to the left of that one. Its light left 240 years ago. The faint smudge near the edge of your vision, that light has been traveling for 2 million years. Every point of light above you belongs to a different chapter of history. You are not looking at the universe. You are looking at an archive. And here is the part that stops most people cold. There is no version of the universe that exists right now, not one that anyone can see, measure, or even meaningfully define. 2 observers on opposite sides of the galaxy cannot agree on what is happening at this moment somewhere else. Einstein proved this. Simultaneity, the idea that 2 events happen at the same time, is not a universal fact. It depends entirely on where you are and how fast you are moving. The universe does not have a shared present tense. Every point in space is living in its own private now, and none of them are synchronized. This is not a limitation of our instruments. It is not something better telescopes will eventually overcome. It is the structure of reality itself, enforced by a single number: 299,792,458 meters per second. That number is the speed of light. And it does something far more radical than simply making things look old. It makes the concept of right now across vast distances completely meaningless. When the James Webb Space Telescope captures images of galaxies 13.4 billion light-years away, it is not showing us distant places. It is showing us a different era entirely, the universe as it was when it was less than 400 million years old, when the first structures were barely beginning to form, when the cosmos looked almost nothing like what surrounds us today. The galaxies in those images no longer exist in that form. Many of them have merged, collapsed, transformed beyond recognition over the billions of years since that light began its journey. What Webb sees is not the universe. It is the universe's childhood photograph. And there is something even stranger buried in all of this. Every time you look at something, anything, you are looking into the past. The screen in front of you right now, the light from it left the surface and reached your eyes in roughly 1 nanosecond. That is a delay so small it is completely meaningless in daily life. But it is still a delay. Technically, you have never seen the present. You have only ever seen light arriving from moments that have already passed at distances that have already been crossed. The present, in a strict physical sense, is something you experience but never directly observe. This is what the speed of light actually does to reality. It does not just slow down information, it makes the universe fundamentally local. Each region of space knows only what has had time to reach it. Nothing can know about events happening right now somewhere else because the signal carrying that news has not arrived yet. The universe is not a single connected system updating itself instantly. It is a vast collection of isolated neighborhoods, each receiving news from the others on a delay determined by distance and the speed of light. No device will fix this. No discovery will change it. It is not a problem waiting to be solved. It is the operating system of existence. If the sun disappeared right now, you would have 8 minutes before the light stopped coming. What would you do with those 8 minutes? How did anyone figure this out? That number, 299,458 meters per second. Where did it come from? How do you measure something moving that fast? The answer starts with one of the most spectacular failures in the history of science. A man standing on a hillside at night holding a lantern, completely convinced he had a plan and absolutely wrong about almost everything except the question itself. In 1638, Galileo Galilei climbed a hill outside Florence with a lantern and an assistant, determined to measure the speed of light. The plan was straightforward. Galileo would uncover his lantern. The moment his assistant saw the flash from a distant hill, he would uncover his own lantern in response. Galileo would measure the time between sending his flash and receiving the reply. Divide the distance by half that time. There is your speed. The logic was sound. The execution was careful. The result was nothing. No matter how far apart they stood, no matter how well trained the assistant, the reply appeared instantaneous. Galileo ran the experiment again and again at greater and greater distances. Nothing changed. The light arrived before he could perceive any delay at all. He was not wrong to try. He was simply using the wrong scale. Light travels so fast that it crosses a gap of several kilometers in roughly 10 microseconds. The fastest human nerve response takes around 250,000 microseconds. Galileo was trying to detect a delay 50,000 times shorter than his measuring instrument could possibly register. It was like trying to weigh a single grain of sand on a bathroom scale. Not a flaw in the method. A flaw in the tools available to the era. His conclusion was honest. Either light travels infinitely fast, or it moves so quickly that no earthly distance can reveal its delay. He suspected the second. He could not prove it. To measure light properly, you would need distances so vast that even light's extraordinary speed would accumulate a detectable lag, distances no hillside in Italy could provide. The solution came 38 years later from a young Danish astronomer doing a job nobody found particularly exciting. Ole Rømer arrived at the Paris Observatory in 1672 with an assignment that sounded more like bookkeeping than discovery track. The orbit of Io, the innermost large moon of Jupiter, and compile precise tables of its Ole eclipses. These tables were important for navigation. Sailors could use Io's clockwork appearances as a reference to determine longitude at sea. It was careful, meticulous, unglamorous work. Rømer was good at it. And after months of careful observation, he noticed something that had no right to be there. The timing of Io's eclipses drifted, not randomly, systematically. When Earth was moving closer to Jupiter in its orbit, Io's eclipses arrived slightly early. When Earth was swinging to the far side of its path, pulling away from Jupiter, the eclipses arrived late. The discrepancy accumulated to roughly 22 minutes across the full width of Earth's orbit. Every other astronomer assumed this was an error in the orbital model. Perhaps Io's orbit was not as perfectly regular as believed. Perhaps Jupiter's gravity introduced subtle variations nobody had accounted for. Rømer looked at the same data and saw something entirely different. The pattern was too clean, too precisely correlated with distance. This was not a flaw in the orbit. This was a message. In 1676, Rømer proposed his interpretation. The eclipses were not arriving early or late. They were arriving exactly on schedule. What changed was how long the light took to cross the increasing or decreasing gap between Jupiter and Earth. When Earth was closer, the light had less distance to cover. When Earth was farther, the journey was longer. The 22-minute total drift was the time it took light to cross the full diameter of Earth's orbit. Light was not instantaneous. It had a finite, measurable speed. Rømer calculated a value of approximately 220,000 kilometers per second. This was about 26% below the correct figure, partly because Earth's orbital diameter was not yet precisely known, and partly due to small timing errors. But the magnitude of the achievement made those imperfections irrelevant. For the first time in human history, someone had proven that light takes time to travel, and that looking at something distant means looking at something past. James Bradley extended the measurement in 1728 through a phenomenon called stellar aberration. As Earth orbits the Sun, the apparent positions of stars shift slightly, not because the stars are moving, but because Earth's own motion changes the angle at which incoming starlight arrives. It is the same effect as rain falling straight down, but appearing to angle toward your face when you run through it. By measuring how much star positions shifted and knowing Earth's orbital speed, Bradley calculated the speed of light to within roughly 1% of the modern accepted value. A remarkable achievement, using only the geometry of starlight and motion. Then came Hippolyte Fizeau in 1849, who did something that sounded ridiculous and worked anyway. Fizeau set up a rapidly spinning toothed wheel with 720 teeth. A beam of light was fired through a gap between teeth, traveled 8 kilometers to a distant mirror, and reflected straight back. If the wheel was spinning at exactly the right speed, the returning beam would arrive precisely when the next tooth had rotated into position and be blocked. By finding the rotation speed that blocked the light, Fizeau could calculate how long the round trip took, and from that, the speed of light itself. Fizeau was essentially playing a game of blink and catch the lightning bolt and winning. The idea sounds almost too simple to work. It worked. This was the first successful measurement of light speed entirely on Earth's surface. No astronomy required, no planetary distances involved. Just a spinning wheel, a mirror, and 8 kilometers of open French countryside. Léon Foucault improved the method the following year, using a rotating mirror instead of a toothed wheel, achieving greater precision. He also discovered something his technique revealed as a byproduct: light travels more slowly through water than through air. This single result overturned Newton's particle theory of light, which had predicted the opposite. Light was definitively a wave phenomenon, faster in less dense media, not faster in denser ones. Albert Michelson refined these rotating mirror techniques over decades, reaching extraordinary precision. He devoted much of his career to measuring the speed of light with meticulous care, eventually winning the Nobel Prize, partly for this work. By the late 19th century, the accepted value had settled at approximately 299,792 kilometers per second in vacuum. The number appeared everywhere, in the equations governing electricity and magnetism, in the mathematics of wave propagation, in the ratio between electrical and magnetic constants that James Clerk Maxwell had calculated and found, to his own surprise, produced exactly the speed of light. Light was not just fast. It was electromagnetic. It was a wave of interacting electric and magnetic fields, and its speed emerged directly from the fundamental constants of those fields. But here was what nobody could explain. Whose speed was it? Sound travels at a speed defined relative to the air carrying it. Waves on water travel relative to the water. Every wave has a medium, and its speed is measured relative to that medium. What was light's medium? What did light travel through? The answer that seemed obvious to every physicist in the 19th century was also the answer that would eventually destroy the most elegant theory they had built. If you were Roma watching, Io arrived 22 minutes late, and realizing what that delay meant, would you have been willing to announce it, knowing that every other scientist would assume you had simply made an error in your tables? Michelson built the most sensitive optical instrument ever, constructed specifically to answer that question. He designed it to detect a difference so small it would be nearly invisible. He found nothing at all. And that absence, that perfect, complete, devastating nothing, did not just challenge 200 years of physics. It erased them. In 1887, Albert Michelson and Edward Morley were not hunting for something small. They were trying to prove that the entire universe, every cubic centimeter of what appeared to be empty space, every gap between the planets, every void between the stars, was filled with an invisible, odorless, untouchable substance that no human had ever directly detected. They were not eccentric. They were not operating on a hunch. They were following the most logical conclusion available to every physicist of their era. Because if light was a wave, and by this point the evidence that it was a wave was overwhelming, then it had to be a wave of something. Waves do not exist in isolation. They are disturbances in a medium. And the medium that light supposedly disturbed had a name, the luminiferous ether. The logic was clean. Sound waves travel through air. Remove the air and sound cannot propagate. Ocean waves travel through water. Drain the ocean and the waves disappear. Light traveled through space, including the vacuum of space between planets and stars, so there had to be something filling that space for the waves to move through. The ether was not a speculation, it was a necessity. Every serious physicist in the world accepted its existence as simply as they accepted the existence of gravity. But the ether had to possess properties that, when examined carefully, bordered on self-contradiction. Light travels at roughly 300,000 kilometers per second. The stiffer, a medium, the faster waves move through it. Steel transmits sound much faster than water because steel is far more rigid. For light to propagate at its extraordinary speed, the ether would need to be millions of times stiffer than the hardest steel ever forged. Yet this same substance offered absolutely zero resistance to the planets moving through it. Earth had been orbiting the Sun for 4.5 billion years without slowing down by a measurable fraction. The ether was simultaneously the most rigid material conceivable and completely frictionless. No real substance behaves this way, but the logic of waves demanded it, so physicists accepted it. What Michelson and Morley built was designed to finally catch the ether in the act of existing. Their reasoning was straightforward. If the ether fills space, and Earth moves through it at roughly 30 kilometers per second in its orbit around the Sun, then from Earth's perspective, there is an ether wind blowing past us. The same way a cyclist feels wind even on a perfectly calm day, simply because they are moving through still air. Light traveling in the direction of Earth's motion through the ether should effectively have a slight tailwind. Light traveling against Earth's motion should face a headwind. The speeds would differ by a tiny but calculable amount. Like swimming the same distance downstream and upstream, the round-trip time is longer when fighting the current, even if the current is gentle. The instrument they built, an interferometer, split a single beam of light into two beams, traveling at right angles to each other, sent each beam to a distant mirror, and recombined them when they returned. If the two beams had traveled at even slightly different speeds, due to their different orientations relative to the ether wind, the recombined beams would be slightly out of phase, creating a characteristic pattern of light and dark interference fringes. The whole apparatus floated on a pool of liquid mercury, which allowed it to rotate smoothly without vibration, letting them test every possible orientation relative to Earth's motion. The instrument was sensitive enough to detect a shift 40 times smaller than the one they expected to find. There was no room for the effect to hide. They found nothing. Not a small effect, not an ambiguous reading, requiring more careful analysis. Absolutely nothing. The interference pattern did not shift. The speed of light was identical in every direction, regardless of how the apparatus was oriented, regardless of Earth's motion. The ether wind did not exist, because the ether itself did not exist. The news hit the physics community like a building collapsing in slow motion. The experiment was repeated. The conditions were varied. Researchers tried different altitudes, different seasons, different apparatus designs. The result never changed. Nothing. Hendrik Lorentz and George Fitzgerald independently offered a mathematical rescue. Perhaps they suggested objects moving through the ether physically contracted in the direction of motion by exactly the right amount to cancel out the expected difference in light travel times. The arm of the interferometer pointing into the ether wind would shorten just enough so that the light returned in the same time as the beam traveling perpendicular. The equations they produced to describe this contraction were correct. Every prediction matched the observations. The mathematics worked. But the explanation was wrong in a way that the mathematics alone could not reveal. Lorentz and Fitzgerald still believed in the ether. They had constructed a physical mechanism to explain why the ether was undetectable. They were describing the right phenomenon with the wrong picture. Henri Poincaré went even further, developing mathematical frameworks that came remarkably close to what Einstein would later publish. Poincaré understood that something deep was happening. He had almost all the tools, but he could not bring himself to abandon the ether entirely. He kept trying to fit the new mathematics into the old framework. Here is what the Michelson-Morley experiment actually proved, and this distinction matters more than almost anything else in the story that follows. It did not prove that the ether does not exist. It proved something stranger and more fundamental. The speed of light does not depend on the motion of the observer or the motion of the source. These are two entirely different statements. The first is a conclusion about a particular substance. The second is a statement about the nature of light and measurement itself. One tells you something is absent. The other tells you something about how reality is structured. The second statement is the one that mattered. It was the locked door. Einstein would find the key not by picking the lock, but by realizing the door was never locked in the first place. It was simply on different hinges than anyone had imagined. If your experiment produces a result that perfectly contradicts every established theory, do you trust the experiment or do you trust the theory? While the greatest minds in physics were constructing increasingly elaborate explanations for why their invisible cosmic medium refused to show itself, a 26-year-old patent clerk in Bern, Switzerland, was thinking about a question he had first asked himself at the age of 16. The question sounded almost childishly simple. But when he finally worked out the answer, space and time turned out to be something no one had ever suspected them to be. Einstein did not solve the ether problem. He threw it away. Not because he had better data, not because he had found a flaw in the Michelson-Morley experiment that everyone else had missed. He threw it away because he decided to ask a completely different question. While everyone else was asking, why can't we detect the ether? Einstein asked, if the speed of light is the same for every observer, regardless of how they are moving, then what must space and time actually be? The answer he arrived at was, this space and time are not the fixed absolute stage on which the universe performs. They are flexible. They stretch, compress, and bend dynamically, continuously, precisely, in whatever way is necessary to guarantee that every observer, in every situation, measures the exact same speed of light. The universe does not enforce a speed limit. It enforces a measurement, and to make that measurement always come out the same, it adjusts everything else. The thought experiment that started this journey came to Einstein when he was 16 years old. He imagined running alongside a beam of light at exactly the speed of light. If he could do that, what would the light look like from his perspective? It should appear as a frozen electromagnetic wave, a wave of electric and magnetic fields suspended perfectly still in space, oscillating but going nowhere. But James Clerk Maxwell's equations, which described electromagnetic phenomena with extraordinary precision, had no such solution. A stationary electromagnetic wave was not a valid outcome of those equations. The mathematics refused to produce it. Either Maxwell's equations were wrong, which seemed unlikely, given how perfectly they described everything else, or the premise of the thought experiment was flawed. Something about the idea of running alongside light at the same speed was not merely difficult, it was incoherent. 10 years later, Einstein understood why. And it required two statements so simple they sound obvious, until you follow their consequences to the end. First, the laws of physics are identical in every inertial reference frame. Someone floating motionless in space, and someone traveling at constant velocity in a straight line, both experience the same physics. There is no experiment they can perform inside their own environment that will tell them which one is really moving. Motion is relative. There is no absolute rest. Second, the speed of light in a vacuum is the same for every observer, regardless of their motion or the motion of whatever emitted the light. Not approximately the same, exactly the same. Whether you are rushing toward the light source, fleeing from it, or sitting perfectly still, the light arrives at 299,792,458 meters per second. Together, these two statements require the universe to behave in ways that no human intuition had ever anticipated. Consider what the second postulate actually demands. You stand still. A beam of light passes you at its full speed. Your friend flies toward that same beam at half the speed of light. Classical physics, the physics of Newton, the physics of everyday intuition, says your friend should measure the light approaching at 1.5 times its normal speed. Two velocities simply add together, but Einstein said no. Your friend measures exactly the same speed you do, the same number, unchanged. How is this possible? Something has to give. If the speed is fixed but the observer is moving, then the distance or the time or both must be adjusting to produce the same ratio. And that is exactly what happens. The universe maintains the constancy of light speed by making space and time themselves behave differently for different observers. The first consequence is time dilation. Moving clocks run slow, not because of any mechanical effect on the clockwork, not because vibration or heat disturbs the gears, but because time itself flows at a different rate for objects in motion. The faster something moves, the more slowly time passes for it relative to a stationary observer. This is not theoretical. Muons are unstable particles created when cosmic rays collide with molecules in Earth's atmosphere at an altitude of roughly 15 kilometers. A muon at rest survives for only about 2.2 microseconds before decaying. Even traveling near the speed of light, a muon should cover no more than about 660 meters before disintegrating nowhere near enough to reach the surface. Yet detectors on the ground record enormous numbers of muons arriving every second. At 99.94% of the speed of light, the time dilation factor is approximately 30. The muon's internal clock runs 30 times slower than clocks on the ground. What feels like 2 microseconds to the muon is 60 microseconds to us, long enough to complete the 15-kilometer journey. Every muon that reaches the surface of this planet is a living confirmation that time dilation is real. Your navigation application depends on the same effect. Global Positioning System satellites orbit at roughly 14,000 kilometers above Earth's surface, moving fast enough that their onboard clocks run slow by about 7 microseconds per day due to their velocity. Gravitational effects add another 45 microseconds per day in the opposite direction for a net discrepancy of 38 microseconds daily. 38 microseconds sounds negligible, but light travels roughly 11 kilometers in 38 microseconds. Without correcting for these relativistic effects every single day, GPS position errors would accumulate at approximately 10 kilometers per day. Every map on every device would be useless within hours. Special relativity is not abstract physics. It runs in the background of your phone. The second consequence is length contraction. Objects in motion shrink in the direction they are traveling. Not because any force is compressing them, not because the atoms are being pushed closer together, but because space itself is shorter for moving observers. A measuring rod flying past at high speed is genuinely shorter than an identical rod sitting still, not apparently shorter. Actually shorter by a factor that depends on velocity. The third consequence is the most famous equation in science. Energy equals mass multiplied by the speed of light squared. Mass and energy are not two different things related by some formula. They are the same thing expressed in different units. The speed of light squared is the exchange rate between them. 1 gram of matter completely converted to energy releases enough energy to power a mid-sized city for more than a day. This staggering number does not come from anything special about light itself. The speed of light appears in that equation because it is the conversion factor between the spatial and temporal dimensions of the universe, the geometric ratio built into the structure of spacetime. Light happens to travel at this speed because photons carry no mass. The speed belongs to the geometry. Light simply occupies it. If time genuinely runs slower, the faster you move, you could theoretically accumulate less biological age on a long, high-speed journey than the people you left behind. But when you returned, everyone you knew would be older or gone. What would you trade for extra time if the price was arriving in a world that had moved on without you? Einstein showed us that the wall exists. He mapped its boundaries with mathematical precision and proved that no amount of energy, no engineering, no force in the universe could push anything through it. But he never answered the deeper question: why does the wall exist at all? Why is space-time built this way? Why this speed and not some other? Special relativity describes the rules perfectly. It cannot explain where the rules came from. The answer does not live inside relativity. It lives somewhere deeper in the realm, where particles do something that no ordinary language has ever been built to describe. The Large Hadron Collider sits in a circular tunnel, 27 kilometers in circumference, buried beneath the border between Switzerland and France. It consumes roughly 200 megawatts of electricity when running at full capacity, comparable to powering a mid-sized city. Its superconducting magnets are cooled to temperatures colder than outer space. It represents the most sophisticated and expensive scientific instrument ever built by human civilization. And with all of that, every megawatt, every magnet, every kilometer of tunnel, it has accelerated protons to 99.991% of the speed of light. 9 parts in 10 billion short of the finish line. And to close that remaining 9 parts in 10 billion, not to reach twice that speed, not to reach some distant hypothetical maximum, but simply to close that final razor-thin gap, would require infinite energy. Not a great deal of energy. Not more energy than the sun produces in a year. Mathematical infinity, the kind that does not get smaller no matter how much you add to what you already have. This is not an engineering problem. It is not a funding problem. No future civilization, no matter how advanced, no matter what exotic power sources they discover, will ever close that gap by adding more energy. The mathematics of space-time itself is what stands there. And mathematics does not negotiate. To understand why, you need to understand a number called gamma. When Einstein worked out the consequences of his 2 postulates, a specific mathematical factor kept appearing in every equation, describing how motion affects mass, time, and length. Physicists call it the Lorentz factor, though it is almost universally referred to simply as gamma. It measures how dramatically space-time distorts for an object moving at a given speed. At rest, gamma equals exactly 1. Everything is normal. Time flows at its standard rate. Length is unchanged. The object's resistance to further acceleration is simply its rest mass. As speed increases, gamma rises. At 10% of the speed of light, gamma is approximately 1.005. Barely different from 1, the universe is nudging back, almost imperceptibly. At 50% of the speed of light, gamma reaches approximately 1.15. The object now resists acceleration about 15% more than it did at rest. Noticeable in precise measurements, but not yet dramatic. At 90% of the speed of light, gamma climbs to approximately 2.3. The same engine that once produced a certain acceleration now produces less than half as much. The object is not heavier in the sense of having more atoms or more matter. Its rest mass has not changed by a single gram, but its resistance to further acceleration has more than doubled. Pushing it faster requires more than twice the force for less than half the result. At 99% of the speed of light, gamma reaches approximately 7.1. Every unit of thrust now achieves roughly 1/7 of what it would achieve at low speeds. At 99.9%, gamma exceeds 22. At 99.99%, it surpasses 70. Each additional 9 in that decimal string multiplies the resistance further, and each multiplication costs exponentially more than the one before. At 99.991%, where the Large Hadron Collider actually operates, gamma is approximately 7,500. Each proton circling that 27-kilometer ring carries kinetic energy equivalent to a flying mosquito. That comparison deserves a moment of pause. A mosquito in flight weighs roughly 2.5 milligrams. A proton weighs about 1.67 times 10 to the power of negative 24 grams. The mosquito outweighs the proton by more than 1,000 trillion times. Yet the proton accelerated to that extraordinary speed carries the same kinetic energy as the insect. That is what a gamma factor of 7,500 does. It multiplies the effective energy of something almost unimaginably small until it matches the energy of something you could swat with your hand. And still, the proton is 9 parts in 10 billion away from the speed of light. And still closing that gap would require infinite energy. At exactly 100% of the speed of light, gamma does not reach a very large number. It does not approach some enormous but finite value that future technology might eventually supply. It becomes mathematically infinite, infinite resistance to acceleration, infinite energy required. The equation does not produce an approximation that breaks down under extreme conditions. It produces a vertical line, a wall with nothing on the other side. What makes this even more profound is that the infinite energy requirement is not a standalone obstacle. It is one face of a single underlying truth that reveals itself differently depending on which angle you examine it from. Look at it from the perspective of time. As a massive object accelerates toward the speed of light, time on board slows down. At the speed of light exactly, time stops completely. A clock aboard such a vessel would not run slowly, it would not run at all. The universe outside would age infinitely, while 0 seconds passed on board. For any object with mass, this is not a destination. It is the abolition of the traveler's existence as a being that experiences duration. Look at it from the perspective of length. As an object accelerates, it contracts in the direction of motion. At the speed of light, that contraction reaches completion. The object's dimension along its direction of travel collapses to 0. A three-dimensional object cannot have 0 thickness in one direction, while remaining three-dimensional in the others. The geometry becomes physically incoherent. 3 different phenomena, 3 different ways of examining the same constraint, 3 faces of the same wall. Infinite energy stopped time 0 length. They are not 3 separate barriers stacked in sequence. They are the same mathematical truth expressed in 3 different languages. Some theorists have proposed a loophole. If ordinary matter cannot be accelerated to the speed of light from below, perhaps there could exist particles that were never below it. Particles born already moving faster than light that would require infinite energy to slow down to the passer speed of light rather than to accelerate up to it. These hypothetical particles have a name, tachyons. Their mathematics would require them to possess what is called imaginary mass, not small mass, not zero mass, but a mass described by the square root of a negative number. Imaginary numbers appear throughout physics as useful mathematical tools, but they do not correspond to measurable physical quantities in the way that real numbers do. No experiment has ever detected a tachyon. No verified theoretical framework successfully incorporates them without generating causal paradoxes so severe they undermine the logical consistency of any universe that contains them. The proposal remains a mathematical curiosity interesting to examine, and currently without any connection to observed physical reality. The barrier is not a regulation. It is not a speed limit sign that a sufficiently powerful vehicle might eventually ignore. It is the structure of space-time, stating in the clearest mathematical language available that there is no territory beyond this boundary for massive objects to enter. Not because the territory is guarded, because the territory does not exist. The Large Hadron Collider consumes the electricity of an entire city to push protons to within 9 parts in 10 billion of the speed of light. And that final gap still requires infinite energy to close. What does it mean that almost there and infinitely far away can describe the exact same position Einstein built the wall? A century of experiments confirmed every brick of it. Particle accelerators, cosmic ray detectors, GPS satellites, atomic clocks flown on airplanes. Every measurement, every test, every apparatus ever pointed at the question has returned the same answer. The wall is real. The wall is absolute. The wall does not have exceptions. But none of this explains why the wall exists. Why does space-time have this structure? Why this particular speed and not some other? Why does the universe enforce a maximum at all? Einstein's equations describe the consequences of the limit with breathtaking precision. They say nothing about its origin. That answer required a different kind of physicist entirely. Someone who, instead of asking which path a particle follows through space, asked what happens when it follows all of them at once. An electron traveling from point A to point B does not choose a path. It takes all of them, simultaneously. Every conceivable route connecting those 2 points, every curve, every detour, every trajectory that geometry permits happens at once. The electron takes the straight path. It takes the path that loops around the moon. It takes the path that spirals out past Jupiter and curves back. It takes paths that double back through time. It takes paths that move faster than light. None of these are rejected before the journey begins. None of them are forbidden from occurring. They all happen, every single one, and the vast majority of them quietly cancel each other out before you ever have a chance to observe anything at all. This is not a metaphor. This is the actual mathematical structure of quantum mechanics, worked out in precise, calculable detail by a physicist who never trusted textbooks and always trusted pictures. Richard Feynman arrived at Princeton in the autumn of 1939 with a habit that baffled his colleagues. When other physicists encountered a difficult problem, they reached for algebraic machinery, long chains of equations, abstract operators, pages of symbolic manipulation. Feynman reached for a pencil and drew something. He reconstructed physics from first principles, almost compulsively, as if he could only trust an idea after he had built it himself from the ground up. His doctoral advisor, John Wheeler, recognized immediately that this was not a learning style. It was a different way of seeing. That way of seeing would eventually crack open one of the deepest crises physics had ever faced. By the 1930s, physicists had built quantum electrodynamics, the theory describing how light and matter interact at the fundamental level. The framework was promising. It described electrons and photons and the electromagnetic force between them. But when physicists tried to use it to calculate anything beyond the simplest possible cases, the equations collapsed into nonsense. Calculate the energy of an electron sitting alone in empty space, accounting for its interaction with its own electromagnetic field. The answer was infinity. Calculate the correction to an electron's magnetic properties from quantum effects. Infinity again. Calculate the probability of almost any interaction. Infinity, infinity, infinity. These were not approximation errors that better mathematics might fix. The infinities were structural. They lived inside the theory itself, built into its foundations. Some physicists concluded that quantum mechanics and special relativity simply could not be reconciled, that the theory was broken beyond repair, and something entirely new would have to replace it. The crisis persisted through the 1930s, through the war years, with no resolution in sight. Feynman's path integral formulation changed everything. His key insight was this: rather than asking which path a particle follows, ask what happens when you consider all paths at once and add up their contributions. Every possible path from A to B contributes a probability amplitude, a complex number with both a magnitude and a phase, where phase describes the orientation of that contribution in mathematical space. The total probability of the electron arriving at B is determined by summing all these amplitudes together. The strange paths, the ones looping through distant galaxies, the ones that seem to violate every classical expectation, contribute amplitudes whose phases rotate extremely rapidly. When you add up contributions from many such paths, their phases point in wildly different directions and cancel each other almost perfectly. The contribution of a path that detours through the Andromeda galaxy is not zero, but when combined with the contributions of all the nearby similar paths, the net result is effectively nothing. The cancellation is not approximate, it is essentially complete. The paths that survive this cancellation are the ones clustered near the classical trajectory, the path that classical physics would predict. These paths have phases that point in roughly the same direction and add together constructively rather than destructively. The electron is most likely found where classical physics says it should be, not because it was forced onto that path, but because every other path cancelled itself into irrelevance. This explained something that had puzzled physicists since quantum mechanics was first developed. Why does a baseball follow a precise parabolic arc while an electron spreads out in a probability cloud? The answer is scale. A baseball consists of roughly 10 to the power of 25 atoms. When you sum the path contributions for an object that massive, the destructive interference of non-classical paths is so thorough and so complete that only the single classical trajectory survives with any meaningful amplitude. Classical physics is not a separate theory that applies to large objects. It is what quantum mechanics becomes when the strange paths have cancelled each other out so thoroughly that only one path remains. An electron is light enough that the cancellation is incomplete. Enough amplitude survives in the non-classical paths to matter. The electron genuinely spreads, genuinely interferes with itself, genuinely arrives in places that a classical particle never could, not because it has special quantum properties layered on top of normal behavior, but because its path sum has not collapsed down to a single survivor. The infinities that had paralyzed quantum electrodynamics for 2 decades did not disappear under this framework. But Feynman, working in parallel with Julian Schwinger at Harvard and Shinichiro Tomonaga in Japan, developed a procedure called renormalization that tamed them. The procedure worked by recognizing that the infinite self-energy of an electron was not something separate from the electron's measured mass. It was already included in what we call the electron's mass, absorbed into the quantity we measure rather than calculated separately from it. By carefully reorganizing how the infinities appeared and identifying which measured quantities already contained them, physicists could extract finite, sensible predictions from equations that initially seemed to produce only nonsense. Feynman was uncomfortable with renormalization philosophically. It felt to him like a procedure that worked without being fully understood. He used it anyway, because what it produced was extraordinary, and the predictions it generated would eventually be tested against experiment with a precision that no theory in the history of science had ever achieved. If an electron genuinely travels every possible path at once, what is it that decides which path you observe when you make a measurement? The remarkable thing is not that the electron travels every path. Any physicist who studies the formalism long enough eventually makes peace with that. The remarkable thing is what happens specifically to the paths that travel faster than light. They are not blocked. They are not penalized. They do something far stranger, and that something is the deepest explanation yet found for why the speed of light limit needs no enforcement. There is no cosmic police force monitoring the speed of particles and issuing violations when something approaches the limit too closely. There is no rule inscribed into the universe from some external authority, no fundamental law handed down that says faster than light motion is prohibited. The universe does not work that way. What actually happens is quieter, more automatic, and far more elegant. The mathematics of quantum reality handles this on its own, and the mechanism it uses is subtle enough that understanding it changes not just how you think about the speed of light, but how you think about the nature of physical law itself. Return to Feynman's path integrals. Every path from A to B contributes an amplitude with a phase. For paths that stay within the speed of light, this phase is a real valued angle. It points in some direction in the complex plane, and when you add up contributions from nearby similar paths, those directions are close enough to align and produce a net contribution to the probability. Now consider a path that includes a segment where the particle moves faster than light. When you calculate the action, the quantity that determines the phase of that path's contribution, something changes. For a path segment where the particle moves faster than light, the action does not produce a real number, it produces an imaginary number, and an imaginary number in the phase of an amplitude does not cause the phase to point in some direction in the complex plane. It causes the amplitude's magnitude to vary exponentially rather than oscillate. Nearby, faster-than-light paths do not have phases pointing in slightly different directions that might partially cancel. They have phases oscillating infinitely rapidly, so rapidly that the cancellation is not partial, but total and absolute. The faster-than-light path does not contribute zero because it was forbidden. It contributes zero because the mathematics of its own phase structure guarantees perfect self-cancellation. It erases itself. This is the distinction that matters enormously philosophically and physically. A prohibited path is still a conceivable path that something prevents. A self-cancelling path is something different entirely. A path whose contribution to reality is exactly nothing, not because of any external constraint, but because of its own internal mathematical structure. The universe does not block faster-than-light travel. Faster-than-light travel simply fails to show up in any observable outcome automatically by the same mechanism that makes all the other strange paths disappear. The comparison that captures this most precisely is geographical rather than physical. Asking why nothing can travel faster than light is like standing at the North Pole and asking which direction is north. The question assumes the existence of something that the structure of the situation simply does not contain. There is no direction north from the North Pole, not because something prevents you from going there, but because the geometry of the sphere means that concept has no meaning at that location. Similarly, faster-than-light contributions to quantum amplitudes do not fail to appear because anything stops them. They fail to appear because the mathematical geometry of quantum amplitudes has no room for them to land. Feynman diagrams make this concrete in a different way. These pictorial representations of particle interactions contain what physicists call virtual particles. Particles that appear in the intermediate stages of a calculation, connecting real particles to real particles through the mathematics of interaction. Virtual particles can carry combinations of energy and momentum that would be impossible for real particles. They can, in a precise mathematical sense, behave in ways that seem to violate constraints that real particles obey. A virtual photon exchanged between two electrons can have properties that no real photon could possess. This initially looks like a loophole. If virtual particles can violate the rules in intermediate steps, why does the final answer always respect those rules? The answer is that virtual particles are not particles at all in any physical sense. They are terms in a calculation pieces of the mathematical sum that represent contributions to the total amplitude. When all the diagrams for a process are summed together, the violations in individual terms cancel each other out. Every physically observable prediction that emerges from the calculation, every number that can actually be measured, respects causality and the speed of light completely. The intermediate mathematical freedom does not produce observable freedom. The system is self-consistent in a way that runs deeper than any individual rule. The precision with which this has been verified is difficult to communicate in ordinary language. Quantum electrodynamics predicts the anomalous magnetic moment of the electron, a quantity physicists call the G-2 factor, to an accuracy of better than 1 part in 1 trillion. 1 part in 1 trillion. If you measured the distance between Hanoi and Ho Chi Minh City, 1,726 kilometers to 1 part in 1 trillion, your measurement would be accurate to within less than 2 micrometers, less than 1/50th of the width of a human hair. That is the level of agreement between quantum electrodynamic theory and experiment. No other theory in the history of science has been tested to this precision and confirmed so completely. Every prediction that quantum electrodynamics makes, including the absolute non-negotiable self-enforcing nature of the speed of light limit, has been confirmed at this level of accuracy. This is not a theory that gets light speed right by assumption. It gets it right as an output, as a consequence of how probability amplitudes combine as a feature of the mathematics that would be there, whether anyone had noticed it or not. Quantum field theory extends this picture beyond electrons and photons to encompass all known particles and forces except gravity. In this framework, particles are not tiny objects moving through space. They are localized vibrations of fields that permeate the entire universe simultaneously. The electromagnetic field exists everywhere. A photon is that field vibrating in a particular way. The electron field exists everywhere. An electron is a localized disturbance in that field. The speed at which disturbances propagate through a massless field is not a rule that someone applied to the theory. It is what the wave equation for a relativistic massless field produces when you solve it. The speed of light emerges from the mathematics, the way a shadow emerges from an object placed in sunlight, not imposed but inevitable. Any attempt to construct a quantum field theory that permits faster than light propagation runs into the same wall from the inside. Probabilities become negative. Probability is a number between 0 and 1. Negative probability is not a small probability. It is a mathematical breakdown. Conservation laws fail. Causality generates contradictions that the formalism cannot resolve. The mathematics refuses to remain coherent. The only quantum field theories that work, that produce positive probabilities that conserve energy and momentum, that do not generate logical paradoxes, are the ones where the speed of light emerges automatically as the maximum speed of any estimate. Causal influence. The limit does not need enforcement because it is not a limit in that sense. It is a structural feature of what it means for quantum mathematics to be consistent with itself. If the speed of light is not a rule imposed on the universe but a consequence of how quantum mathematics works, does that change what you think a law of physics actually is? Quantum electrodynamics proves that no faster than light path contributes anything to observable reality. The mathematics erases them automatically, completely without exception. But quantum mechanics still contains something that looks at first glance like it breaks this conclusion entirely. Two particles separated by any distance, coordinating instantaneously. no signal, no time delay. Einstein called it spooky action at a distance and spent years insisting it proved the theory was incomplete. He was wrong, and the reason he was wrong is one of the most precisely examined and deeply strange results in the history of physics. Two particles are created together, then separated. One is in Hanoi, one is in New York. You measure the particle in Hanoi and find its spin pointing up. At that exact moment, no delay, no signal traveling between them, no communication of any kind, the particle in New York becomes spin down. Not probably spin down. Not spin down a moment later after some influence has had time to propagate. Spin down instantaneously, regardless of the distance separating them, regardless of whether that distance is a meter or a billion light years. This has been confirmed experimentally, repeatedly, with increasing precision over 4 decades. And it does not violate the speed of light. The way it manages not to violate the speed of light is subtle enough that it took some of the greatest minds in physics decades to work out completely. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a paper arguing that this instantaneous coordination was proof that quantum mechanics was incomplete. Their reasoning went like this: if measuring one particle instantly determines the state of another particle far away, then either some influence traveled faster than light, which Einstein considered impossible, or the particles already had definite states before any measurement was made, and quantum mechanics simply failed to describe those pre-existing states. There had to be hidden variables, predetermined answers carried by each particle from the moment they were created, like two gloves separated into different boxes. Open the box in Hanoi and find the left glove, you instantly know the box in New York contains the right glove. No mystery, no faster-than-light influence, just information you already had without knowing it. The glove analogy is clean and satisfying. It is also wrong. And the proof that it is wrong came from a theoretical physicist in 1964 who asked a question no one had thought to ask before. John Bell realized that hidden variables and genuine quantum entanglement make different numerical predictions. If particles carry predetermined hidden states, the correlations between measurements made at different angles on the two particles must satisfy a specific mathematical inequality now called Bell's inequality. If quantum mechanics is correct and no hidden variables exist, those correlations should violate the inequality. The question of whether reality is classical underneath or genuinely quantum was no longer a philosophical debate. It was a testable experimental question. Alain Aspect and his team performed the decisive test in 1982. Bell's inequality was violated. Definitively. Subsequent experiments over the following decades closed every remaining theoretical loophole one by one. In 2022, the Nobel Prize in Physics was awarded to Aspect John Clauser and Anton Zeilinger specifically for their experimental work, establishing the reality of quantum entanglement beyond any reasonable doubt. No hidden variables exist. The particles do not carry predetermined answers. Einstein was wrong about this particular point. The correlation is real and it is instantaneous. So how does it not violate the speed of light? The answer lies in what you can actually do with the correlation. When you measure the particle in Hanoi, you get a result, spin up or spin down with equal probability, 50% chance of each. You have no control over which result you get. The outcome is genuinely random, not pseudo-random in the way a coin flip is random because you lack information about the physics. Fundamentally, irreducibly random. You cannot choose to get spin up. You cannot force spin down. The result happens to you. Your counterpart in New York measures their particle and also gets a random result. From their perspective, without any outside information, their sequence of results looks like pure noise, completely random, uniformly distributed, no pattern, no signal. To discover that the two sets of results are correlated, that every time you got spin up they got spin down, you must compare your measurement records. And that comparison requires ordinary communication. A phone call, an email, a radio signal, something that travels at the speed of light or slower. The correlation exists instantly. The knowledge of the correlation cannot exist until classical information has traveled between the two locations. This distinction between non-local correlation and non-local information is not a technicality physicists use to avoid an embarrassing conclusion. It is the precise mathematical content of what physicists call the no communication theorem. The theorem demonstrates rigorously that quantum entanglement cannot be used to transmit information faster than light under any circumstances, not with better technology, not with more carefully prepared particles, not with cleverer measurement strategies. The mathematics rules it out completely. The universe permits non-local connection. It does not permit non-local information. The universe is more subtle here than any simple rule would allow. The correlation is immediate. The meaning of the correlation is not. Quantum tunneling offers another apparent crack in the speed limit that closes upon careful examination. A quantum particle approaching an energy barrier it classically cannot surmount sometimes appears on the far side anyway, not by going over the barrier or around it, but by tunneling through it in a way that has no classical analog. In some experiments, the peak of the transmitted wave packet appears to emerge from the far side of the barrier before the peak of the incoming wave packet has fully entered. Measured carelessly, this looks like the packet traveled faster than light through the barrier, but information is not carried by the peak of a wave packet. Information is carried by the front edge, the very first part of the wave to arrive, which establishes that something is coming at all. The front of the transmitted wave packet never emerges before causality permits. What moves apparently faster than light is the phase velocity of the wave, the speed at which the peaks and troughs of the oscillation move. What carries actual information is the group velocity, the speed at which the overall envelope of the packet travels. These two velocities are different quantities, and only the group velocity is constrained by the speed of light. Every experiment that initially claimed to observe faster-than-light tunneling examined carefully confirmed that no actual information had traveled faster than light. The phase raced ahead. The signal did not. The universe, it turns out, is extraordinarily consistent about this. Every apparent loophole entanglement, tunneling every effect that initially seems to threaten the limit, closes in exactly the same way. The correlation or the effect is real, but the information stays behind, traveling at the speed of light or slower every single time. If two entangled particles genuinely coordinate instantaneously across any distance, what does that say about what space actually is between them? Every theoretical escape route has been sealed, but the human mind does not surrender to mathematical constraints without first trying to go around them. There are proposals that do not attempt to move through space faster than light, but instead propose bending space itself, rewriting the geometry of the journey so that the distance simply ceases to be what it was. The mathematics of general relativity technically allows this. The price that physical reality demands for it is something else entirely. In 1994, a physicist named Miguel Alcubierre published a paper that caused considerable excitement and continues to appear in science fiction with pleasing regularity. His proposal was elegant in its framing. A spacecraft does not need to travel faster than light. It needs to arrange for space itself to travel around it. Contract the space in front of the ship, expand the space behind it, and the vessel rides a wave of distorted space-time, like a surfer on a wave stationary relative to its immediate local environment, while that environment moves. Locally, nothing exceeds the speed of light. The ship does not accelerate through space at all. It simply sits inside a bubble while the bubble relocates. Globally, enormous distances are covered in whatever time the space-time manipulation requires. The mathematics of Einstein's general relativity does not forbid this. The equations that describe how space-time curves in response to energy and mass to permit solutions, where the metric, the mathematical description of space-time geometry, has exactly the form Alcubierre described. On paper, the idea works. The question is what physical reality requires to make the paper match the universe. The first requirement is exotic matter material with negative energy density. Not matter with low energy, not matter with zero energy. Matter whose energy density is a negative number, which means it gravitationally repels rather than attracts. The Casimir effect demonstrates that quantum mechanics permits small regions of negative energy between closely spaced conducting plates, and Hawking radiation involves related phenomena. But the quantities involved are extraordinarily small, far smaller than what any warp bubble geometry requires. Early estimates of the exotic matter needed to sustain even a modest warp bubble placed the requirement at roughly the mass-energy equivalent of the planet Jupiter, expressed as negative energy. Subsequent refined analyses reduced this estimate, but could not bring it anywhere near quantities that observation or experiment suggested were accessible. The gap between what is theoretically permitted in tiny quantum contexts and what the warp drive requires in macroscopic quantities remains essentially unbridgeable with any physics currently understood. The second problem is control. Any signal generated inside the warp bubble travels at the speed of light relative to the local space inside the bubble. The front wall of the bubble is moving from the perspective of the outside universe faster than that local light speed, which means no signal from inside the bubble can ever reach the front wall. The pilot cannot steer, the pilot cannot brake, the pilot cannot communicate with the leading edge of their own transportation system. A warp drive, if it could be built, would be a vehicle with no steering wheel and no brakes launched on a trajectory that could not be modified after departure. The third problem is what accumulates at the front of the bubble during travel. As the bubble moves, it sweeps up particles and radiation from the space ahead of it. These particles, blue-shifted by the bubble's motion, accumulate into an increasingly energetic concentration at the leading edge. When the bubble eventually stops by whatever mechanism, since the pilot cannot control this, that stored energy releases. Calculations suggest the released energy could be sufficient to destroy the destination system. The warp drive arrives and sterilizes everything it came to visit. Wormholes present a structurally different approach that encounters structurally similar obstacles. Einstein and Nathan Rosen identified in 1935 that the mathematics of general relativity permits solutions connecting two distant regions of spacetime through what amounts to a shortcut, a tunnel threading through or around the space between them. Enter one mouth, exit the other mouth, having crossed a distance that light traveling through normal space would take years or centuries to cover. The immediate problem is stability. An unmodified Einstein-Rosen bridge collapses essentially instantaneously. It closes faster than light can cross it. Keeping it open requires again exotic matter with negative energy density positioned at the throat of the wormhole to prevent the geometry from pinching shut. The quantities required are again enormous relative to anything quantum mechanics has produced in any observed context. Natural wormholes, if they exist at quantum scales, would have sizes on the order of the Planck length, approximately 10 to the power of -35 meters. This is smaller than a proton by a factor of roughly 10 to the power of 20. Expanding such a structure to human traversable size while maintaining stability would require physics that does not currently exist even as a theoretical framework. Every proposed shortcut around the speed of light limit converges on the same final obstacle: exotic matter with negative energy density at scales that no known physics can produce. This is not coincidence. It reflects something deep about the structure of space-time. The mathematics of general relativity contains these solutions because mathematics explores all self-consistent geometries. Physical reality selects from among those geometries based on what actual energy and matter can create. The solutions that require impossible matter are not blueprints waiting for better engineering. They are mathematical objects that describe geometries the physical universe does not appear to instantiate. What is actually happening, viewed from the deepest level, is this. There is no path in the mathematical structure of spacetime that connects the region of velocities below the speed of light to the region above it for any object with mass. Not a blocked path, not a difficult path. The connection simply does not exist in the geometry. It is not a wall, it is an absence. There is nothing on the other side to reach. If both warp drives and wormholes require matter with properties that have never been observed, does that suggest our understanding of physics is incomplete, or that the universe simply has no interest in being crossed? Every door is closed. But something strange emerges when you step back and look at the whole picture. The speed of light limit is not a prison confining us to a small corner of a vast cosmos. It is the very thing that makes us possible in the first place. To understand why you have to look at the largest thing imaginable, the full history and future of the universe itself, there are galaxies whose light is currently on its way to Earth. That light has already been traveling for billions of years. It left its source long before our solar system existed, crossed distances that make the human mind go quiet, and it is still coming, still racing toward us at 299,792 kilometers per second through the dark. And it will never arrive, not because something stopped it, not because anything blocked its path, but because the space between those galaxies and us is expanding faster than light can cross it. Those galaxies have already slipped beyond our cosmic horizon, permanently, irrevocably, forever. And every day that passes, more galaxies cross that line and vanish from our universe as completely as if they had never existed. This is not a future event to be concerned about. It is happening right now, continuously, in every direction. The observable universe, the region from which light has had time to reach us since the beginning, extends roughly 46 billion light-years in every direction. This number confuses people immediately because the universe is only 13.8 billion years old. If light has been traveling for 13.8 billion years, how can anything be 46 billion light-years away? The answer is that space itself has been expanding throughout that entire journey. Light that left a distant region 13 billion years ago traveled through space that was stretching as the light crossed it. By the time that light finally arrives here, the region that emitted it has been carried much farther away by the cumulative effect of expansion. The source of ancient light we receive today now sits tens of billions of light years from us, even though the light itself only traveled for a fraction of that time. The boundary where galaxies are receding from us at exactly the speed of light is called the Hubble horizon. Beyond it, galaxies are moving away faster than light, not because they are traveling through space at superluminal speeds, which special relativity forbids, but because the space between us and them is growing faster than light can cross. The distinction is crucial and frequently misunderstood. No object moves through its local space faster than light. The space itself is what moves. General relativity permits this. The speed limit applies to motion through space, not to the expansion of space itself. What drives this expansion is dark energy, a component of the universe that constitutes roughly 68% of its total energy content, and whose fundamental nature remains completely unknown. Physicists know it exists because the expansion of the universe is accelerating rather than slowing down. Something is pushing everything apart with increasing urgency. What that something is, where its energy comes from, why it has the particular density it has, none of these questions have answers that current physics can supply. Dark energy is the largest constituent of the universe and the least understood object in science. Its consequence for the long-term future is stark. As expansion accelerates, more and more galaxies cross the Hubble horizon and disappear from the observable universe permanently. In approximately 100 billion years, only the local group, the roughly 50 galaxies gravitationally bound together in our immediate cosmic neighborhood, including the Milky Way and Andromeda, will remain visible. Every other galaxy in the observable universe will have crossed beyond the horizon, their light red-shifted into silence, their existence undetectable by any instrument. The astronomers of that distant era will inhabit a cosmos that looks nothing like ours. They will see a single gravitationally bound island of galaxies surrounded by perfect, featureless darkness. The cosmic microwave background radiation, the ancient light left over from the hot early universe, which tells us today so clearly that the universe began in an extremely hot and dense state, will have been stretched by expansion into wavelengths so long they fall entirely below any reasonable detection threshold. The evidence of the Big Bang will be gone. The pattern of galaxy distribution that reveals cosmic expansion will be gone because all visible galaxies will be moving toward each other under mutual gravity, rather than away from each other with the universal flow. Future astronomers, working with only what their instruments can detect, might reasonably conclude that they live in a static island universe of modest size, eternal and unchanging. They would be wrong in every particular, and they would have no way to know it. This is the most unsettling lesson the disappearing universe teaches. Our current understanding of cosmology, the Big Bang, cosmic expansion, the age and scale of the universe, is possible only because we happen to exist at a moment in cosmic history when the evidence is still visible. We live in an era of cosmic privilege, when enough of the universe's history has unfolded to be readable, but not yet so much time has passed that the evidence has been swept beyond the horizon. The window is open now. It will close. The speed of light does not just limit what we can reach, it limits what we can know. Every horizon in the universe is ultimately a horizon of information, a boundary beyond which nothing can tell us anything, because no signal has had time to arrive or ever will. In September of 2015, the LIGO observatories detected gravitational waves for the first time. Ripples in space-time generated by two black holes colliding 1.3 billion light-years away. The signal, when it arrived, lasted a fraction of a second, but it carried enough information for physicists to measure the propagation speed of gravitational waves with extraordinary precision. The result: gravitational waves travel at the same speed as light, matching it to better than 1 part in 1 million billion. Gravity and electromagnetism, two completely different forces, described by completely different mathematical frameworks, propagate at exactly the same speed. Not approximately the same, identical. This is not a coincidence about light specifically. Both forces travel at the speed of causality, the fundamental maximum rate at which any influence can propagate through spacetime. Light happens to share this speed because photons are massless. Gravitational waves share it for the same reason. The speed does not belong to either force. It belongs to the geometry of spacetime itself. Black holes represent the most extreme expression of what the causal speed limit does to spacetime geometry. The event horizon of a black hole is not a physical surface. No membrane, no barrier, no wall of any material substance marks the boundary. It is a causal horizon, a surface in spacetime beyond which every possible path through space and time leads inward toward the singularity. Below the event horizon, moving away from the center is not merely difficult or energetically costly. It is geometrically impossible in the same way that moving backward in time is geometrically impossible in normal spacetime. The structure of spacetime inside the horizon simply does not contain any outward leading paths. Not blocked paths, absent paths. If 100 billion years from now, future astronomers cannot see any evidence of the Big Bang, what does that tell us about the relationship between scientific truth and the ability to observe it? The speed of light decides what we can see, but it goes far deeper than that. It decides why time has a direction, why the past is the past, why cause always comes before effect. And when you understand that, you realize that without the speed of light, there would be no you to ask this question. Pick up a teacup and drop it. It shatters on the floor. You have never seen the reverse happen. You have never watched ceramic fragments leap from the floor, assemble themselves into a cup, and land intact in a waiting hand. Yet the fundamental equations governing the behavior of every atom in that cup are almost perfectly symmetric in time. Run them forward, and the cup falls and breaks. Run them backward, and the mathematics remains valid, every force balanced, every conservation law satisfied, every equation of motion obeyed. The physics does not care which direction time flows. The physics works either way, but you only ever see it flow one way. Shattered cups do not reassemble. Cold coffee does not spontaneously reheat. Smoke does not gather itself back into unburned wood. Something in the universe picks a direction and insists on it with absolute consistency, even though the deepest equations of motion contain no such preference. Why? The answer connects directly to the speed of light, and it runs deeper than most accounts of entropy and thermodynamics acknowledge. The second law of thermodynamics states that, in any closed system, entropy is the measure of disorder. The count of microscopic arrangements compatible with a given macroscopic state tends to increase over time. A broken cup has vastly more possible arrangements of its atoms than an intact cup. Once broken, the probability of spontaneously returning to the intact state is not zero in principle. It is simply so astronomically small that in the age of the universe it has never been observed. Disorder increases because there are overwhelmingly more disordered states than ordered ones. And random processes explore states with probability proportional to how many of each kind exist. But this statistical argument explains why entropy increases. It does not explain why entropy increases toward the future rather than the past. The statistics apply equally in both directions. Yet we remember the past and not the future. Causes precede effects and never follow them. The arrow points consistently one way and never the other. The light cone structure of space-time provides the geometric foundation for this asymmetry. Every event in the universe sits at the apex of two cones, extending through space-time, one opening toward the future, one opening toward the past. The future light cone contains every event that this event could potentially influence, given that any influence can travel at most at the speed of light. The past light cone contains every event that could potentially have influenced this one. Everything outside both cones, the region of space-like separation, is causally disconnected. No signal, no force, no influence of any kind can connect this event to those regions. Physicists classify the relationship between any two events using this geometry. Events separated by a time-like interval, where the time between them is large enough that light could travel between them, can be causally connected. Every observer, regardless of their motion, agrees on which event came first. Causal order is absolute for time-like separated events. Events separated by a space-like interval where the spatial distance between them is too large for light to cross in the available time cannot be causally connected. And crucially, different observers moving at different velocities can disagree about which of two space-like separated events occurred first. Neither ordering is more correct than the other. The universe simply does not define an objective sequence for events that cannot influence each other. This is the geometric foundation of why time has a direction. Causality is only defined within the light cone, and the light cone is defined by the speed of light. Remove the finite speed of light, and the entire structure collapses. Consider what a universe with infinite light speed would look like. Every event would fall within the light cone of every other event. Everything could potentially influence everything else instantaneously. Temporal ordering would become absolute and universal. No observer disagreement, no relativity of simultaneity. This sounds appealing. But the causal structure would generate paradoxes without resolution. If every event can influence every other event across all of time simultaneously, the logical consistency of cause preceding effect breaks down completely. You could not construct a coherent narrative of what causes what, because every event would be simultaneously cause and effect of every other. At the opposite extreme, a universe where the speed of light is zero would contain no causal connections at all. Every event would be space-like separated from every other. No signal could propagate. No force could act across any distance. The universe would be a collection of completely isolated points, each experiencing nothing, affecting nothing, knowing nothing of any other. No physics, no chemistry, no stars, no life. The actual speed of light, 299,792,458 meters per second, sits at a value that makes something possible which neither extreme permits. A universe with causal structure, rich enough for complexity to emerge, but limited enough that logical consistency is maintained. Stars can burn for billions of years because nuclear reactions release energy at rates compatible with this speed. Planets can cool and develop chemistry because thermal processes operate on timescales set by this speed. Life can evolve through countless generations because the causal chains linking parent to offspring environment to adaptation persist across deep time without paradox. Consciousness itself depends on this structure in a way that is rarely stated directly. Every thought you have is a causal chain, neurons firing in sequence, each activation caused by previous activations, the whole process unfolding in time with strict before and after ordering. Memory stores the past and not the future because causal influence flows in one direction only. Decisions produce consequences rather than being produced by them. The experience of being a self that persists through time, that remembers, that anticipates, that chooses all of it, rests on the foundation of causality. And causality rests on the light cone, and the light cone is drawn by the speed of light. There is a dimensionless number called the fine structure constant, approximately equal to 1 divided by 137, which connects the speed of light to the electron's charge, and Planck's constant, the fundamental quantum of action. Feynman called this number the greatest mystery in physics. Nobody knows why it has the value it has. No theory derives it from first principles. It must be measured. But change it by more than a few percent, make it 4% larger, and carbon cannot be synthesized in stellar cores through the triple alpha process that builds carbon from helium. Without carbon, the chemistry of life as we understand it does not exist. The fine structure constant, the speed of light, the charge of the electron, and the existence of carbon-based life are bound together in a relationship so precise that a small shift in any one element breaks the chain. If the speed of light were twice as large, what would the universe look like? And could life of any kind survive in it? The speed of light creates causality. Causality creates the direction of time. The direction of time creates the concepts of before and after, create memory. Memory creates consciousness. Consciousness creates this question. And that question leads to a final understanding that very few people stop long enough to consider. From Galileo standing on a hillside outside Florence with a lantern, to Roma watching Jupiter's moon arrive late, and understanding why, to Michelson, finding nothing in what should have been full, to Einstein, dismantling space and time, with two quiet postulates to Feynman, demonstrating that the universe self-censors its own faster-than-light contributions. Through the mathematics of quantum amplitudes, every step of this journey, spanning nearly 4 centuries of human inquiry, converges on a single recognition. The longer you sit with it, the more staggering it becomes. Light does not own the speed it travels at. This sounds like a small point. It is not. Photons move at 299,792,458 meters per second. Not because that speed belongs to them, not because something about the nature of light requires that particular velocity, but simply because photons have no mass. In the geometry of space-time, massless particles have exactly one option available to them. They travel at the maximum causal speed. They cannot go slower, they cannot stop. The speed does not describe light. Light merely occupies it the way a river occupies the lowest available path through a landscape. The path existed before the river. The river did not create the path. Calling it the speed of light is, in a precise sense, a historical accident, a name attached to a number, because light was the first thing we measured, traveling at that speed, not because the number has anything specifically to do with electromagnetic radiation. A more accurate name would be the speed of causality, or the speed of information, or the rate at which the universe updates itself. Any of these captures what the number actually represents: the maximum velocity at which a cause can produce an effect anywhere in the cosmos. This is why the same number appears throughout physics, in contexts that have nothing obvious to do with light. Gluons, the particles that carry the strong nuclear force, binding quarks together inside protons and neutrons, are massless, and they travel at this speed within the confines of atomic nuclei. Gravitational waves travel at this speed, as LIGO confirmed in 2015, with a precision of better than 1 part in 1 million billion. If gravitons exist as the quantum carriers of gravity, they would be massless, and they would travel at this speed. Every force carried by a massless particle must propagate at exactly this velocity. Not approximately, exactly, because the speed does not belong to any of these forces individually. It belongs to the geometry of space-time that all of them inhabit. The most famous equation in science carries the same truth in compressed form. Energy equals mass multiplied by the speed of light squared. This equation is almost universally misread as a statement about nuclear energy or the relationship between matter and radiation. It is neither. It is a geometric statement. Mass and energy are not two different things that happen to be related by a formula. They are the same thing, measured in different units, the way temperature measured in Celsius and temperature measured in Fahrenheit describe the same physical reality through different numerical conventions. The speed of light squared is simply the conversion factor between mass units and energy units, the exchange rate built into the geometry of space-time. It appears in that equation not because light is involved in the conversion, but because the speed of light is the ratio that relates the spatial and temporal dimensions of the universe to each other. The equation would look exactly the same in a universe where photons had never existed, as long as that universe had the same space-time geometry as ours. What Feynman actually uncovered was something that goes beyond even this. The speed limit does not appear in the quantum description of nature as a rule that someone decided to impose and then wrote into the equations. It emerges from within. When you sum the probability amplitudes for all possible paths a particle might take, the mathematical structure of that sum automatically produces zero contribution from any path containing faster-than-light segments. No enforcement mechanism is required. No external authority maintains the limit. The universe is self-consistent, and self-consistency demands a maximum causal speed. That speed is what we call the speed of light. The limit is not a constraint on what the universe permits. It is a consequence of what it means for the universe to be coherent at all. And here, the story reaches a boundary that current physics cannot cross. Why is the speed of light 299,792,458 meters per second, rather than some other value? Why not twice that? Why not half? The honest answer, stated plainly, is that no one knows. The fine structure, constant the masses of the fundamental particles, the speed of light. These are numbers that must be measured. They cannot be calculated from deeper principles. No theoretical framework currently in existence derives them from first principles and predicts their observed values before measurement. They sit at the foundation of physics as brute empirical facts accepted because measurement finds them there unexplained by any theory we have. This is not a temporary gap waiting to be filled by the next generation of physicists. It may be the deepest limit of what physical explanation can achieve. Explanation works by showing that one thing follows from another. But the chain of explanation must end somewhere. It must rest on something that is simply the case without being derivable from anything more fundamental. The speed of light may be one of those terminal facts, a feature of reality that does not follow from anything deeper, but on which everything else depends. The anthropic principle offers a partial and unsatisfying response to this silence. We observe this particular speed of light. It suggests because we exist, and we exist only because the universe's fundamental constants fall within the narrow ranges that permit observers to arise. Change the speed of light enough, and the fine structure constant shifts with it. Change that enough, and carbon cannot form in stellar cores. No carbon, no organic chemistry, no life of the kind we represent. We observe this speed because only in a universe with something close to this speed can there be anyone to observe anything. This is not an explanation of why the speed has its value. It is a recognition that we should not be surprised to find ourselves in a universe where the value permits our existence. The question of why this value, rather than another, remains open, sitting at the frontier of physics and philosophy, currently unanswered. The circle, when you see it whole, is breathtaking in its completeness. Without a finite speed of light, there is no causal structure. Without causal structure, time has no direction. Without directed time, entropy cannot increase in any consistent sense. Without entropy, increase the thermodynamic processes that drive chemistry cannot proceed in any coherent way. Without complex chemistry, no molecules capable of storing and replicating information can form. Without such molecules, no life. Without life, no consciousness. Without consciousness, no capacity to ask why anything is the way it is. The limit you might instinctively want to break is the limit that built you. The barrier is not something imposed on you from outside your nature. It is woven into the fabric of what you are. Every neuron in your brain fires in sequence rather than simultaneously because causal signals travel at finite speed. Every memory you carry records the past rather than the future because information flows in one direction only. Every decision you make produces consequences rather than being produced by them because cause precedes effect in a universe with a finite causal speed. The thing that seems to confine us is the thing that makes the word us meaningful. If the speed of light is what makes existence possible, does that change how you think about limits? Galileo stood on a hillside with a lantern, wanting to catch the light. He failed. But the journey that began with that failure through 3 centuries, through thousands of experiments, through the greatest minds our species has produced, arrived here. Light cannot be caught, not because it is too fast, but because it is the heartbeat of reality itself. And you cannot stand outside the heartbeat of the thing that is creating you.